So today we're going to talk about bonding. James bonding. I'm sorry, that was really lame. But anyway, bonding is important because this is where we actually start to bring together the atoms and to form these into molecules and compounds. Now the first thing that we need to define would be the law of constant composition, which is pretty simple. It just means that pure substances have constant composition. Or in other words, if I have a sample of water from a drinking fountain here in Haverhill, and I check that, it's going to have the formula H2O, 2 parts hydrogen to 1 part oxygen. What if I go to the Gulf of Mexico and get a sample of water there? It's going to be H2O. If I go to a glacier up in Nova Scotia, it's going to be H2O. Okay, constant composition. Now, what that also means is that mixtures are going to have variable compositions. Those can change, right, depending on what you put in. It's kind of like your favorite cookie recipe. You might add in a little extra vanilla this time or a few extra chocolate chips because the mixtures can vary in their composition. Now, a few more definitions that we should have would be compounds. Compounds are pure substances. Okay, they're formed by chemically combining 2 or more elements. This is different than a mixture because in a mixture you've only physically combined things. You mix them together, but you can physically separate them. So for example, if you go to Taco Bell for a 7-layer burrito, you could open it up and you could pull out the tomatoes or the rice and so forth because they've just been physically combined. But if I have a sample of something like H2O, there's no way that I could just physically walk in with a pair of tiny tweezers and pluck off the oxygen atom. It doesn't work because this is a compound. You'd have to do some kind of chemical reaction to break apart the hydrogen and the oxygen. Now what I just wrote here, H2O, is what's known as a chemical formula. It's a shorthand method of writing chemicals. It gives the element symbols and the subscripts, and it's very important to note that the subscripts tell you how many of each atom you have. So in this case we have 2, and that refers to the hydrogen. So 2 hydrogens, and how many oxygens? Well, just 1. If there's no number written here, it's implied it's a 1. You won't see things written with a 1 there. Okay. Or in other words, if I had something like C4H10, that would have 4 carbons and 10 hydrogens, right? Simple chemical formulas. Now, we can actually classify material in different ways. Okay, we can actually classify these as either elements or compounds. It's important to remember that elements are what you find on the periodic table. This would be something like sulfur or gold or lithium or astatine or any of the just elements that are on the periodic table. Compounds, on the other hand, compounds are actually a mixture of 2 or more elements chemically combined. So H2O has hydrogen and oxygen. So it's not an element, it's made of elements. It's a compound. Or something like sodium chloride, which is table salt. Again, it has 2 or more elements chemically combined. Now we can actually take the elements and we can classify these as either atomic elements or molecular elements. As the name implies, atomic elements are just atoms. They just hang out by themselves, right? They're just single atoms. Molecular elements, those atoms like to form molecules. So for instance, oxygen, the air that we breathe, the oxygen in the air that we breathe isn't just pure oxygen atoms floating around, right? Those oxygen atoms always like to pair up with each other. So you'll actually find them in the form of O2, right? Because this is a molecular element. So it's just O2. Whereas if you wrote the formula for gold, it's just AU. It's just a single, atom of gold. Whereas oxygen likes to partner up with itself. Now, what about compounds? Compounds have to be 2 or more elements, and it's important that we notice some differences here. Okay, one is that molecular compounds are made of only nonmetals. All right, so this would be something like H2O, hydrogen and oxygen, both nonmetals. Remember that the nonmetals are in the top right-hand corner of the periodic table. So if I do a really crappy periodic table over here, where would our nonmetals be? They would be these guys up in the top right-hand corner, except for hydrogen, which is over here. Okay. So if you have something that's made of just nonmetals, something like C6H12O6, which is glucose, carbon, hydrogen, oxygen, all nonmetals. Therefore, this is a molecular compound. Now, on the other hand, something like table salt, which is sodium chloride, or NaCl, contains a metal, metals on the left-hand side of the periodic table, and also these guys way down here. Okay, so those are all metals. Sodium's a metal. Chlorine, on the other hand, is a nonmetal up in the top right-hand corner. So this would be an ionic compound because it has a metal and one or more nonmetals put together. Okay, so how do we know which of the elements are molecular elements? Well, there are a couple of ways. Some textbooks like to talk about something called the rule of sevens, which sounds like something out of a Sith Lord movie or something. So instead what I like to do is two different methods, right? One method is by spelling Brinkelhoff, okay? And that will actually help you remember these. So we've got bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those are the 7 diatomic elements. And by diatomic, I mean that these like to exist in pairs, right? So bromine doesn't exist by itself. It'll always pair with itself to make bromine, diatomic bromine, Br2, or O2, or F2. Now, these could obviously be paired up with something else. Hydrogen and oxygen make water and so forth, but if it's just oxygen by itself, it'll always be O2. So Brinkelhoff is how I typically remember it because it's easy. It sounds like David Hasselhoff, Knight Rider, so that's easy to remember. The other method that some people like is to actually remember the gens. Okay, so what does that mean? Well, that means that you've got hydrogen, oxygen, nitrogen, and then the halogens. Remember, those are in column 7A. So they all end in gen, and so if you prefer, remembering that, then either one totally works. Whichever works best for you is what you should do. What I do want you to remember, though, is that if something is not a molecular element, it's just going to be an atomic element. So if I say bromine, molecular or atomic, you'd say, oh wait, Brinkelhoff, yeah, bromine's one of those diatomic ones, so that must be a molecular element. But if I say something like strontium, you'd say, strontium's not part of Brinkelhoff, so that must be an atomic element, and you'd be right. All right, what's the next thing that we need to worry about? Well, we need to start looking at the compounds themselves. So a compound, remember, means 2 or more elements chemically combined. Now, in a molecular compound, these things are held together by what are known as covalent bonds. So a covalent bond, what you need to remember is that this is a sharing of electrons, okay? Not a transfer, just a sharing of electrons. These typically form between 2 nonmetals, or if you have a nonmetal and a metalloid. So, for instance, in methane, you have carbon and hydrogen bonds. And you'd say, oh, so CH4 is methane. That must be a molecular compound because carbon and hydrogen are both nonmetals. Okay, or something like N2O4. All right, nitrogen, oxygen, both nonmetals. Therefore, this must be a molecular compound. And technically, we could call these molecules because this is a discrete group of atoms that's sharing electrons. Remember, sharing means a covalent bond. Now, besides having molecular compounds, we could have ionic compounds. And these, as the name implies, are held together by ionic bonds. Now, ionic bonds are a transfer of electrons. All right, so if you have something like sodium chloride, it's not like sodium and chlorine are happily sharing, some electrons. Instead, what happens is the chlorine literally rips away an electron from the sodium. So you have chlorine, or in this case actually chloride, because it has a negative charge, and then sodium cation with a plus charge. And then because you have a positive and a negative, then these things are attracted to each other, and so they end up binding together to form sodium chloride. Alright, so that's an ionic compound. We can see the same thing down here in this chemical equation. So our chemical reaction, magnesium and oxygen, metal, non-metal. All right, these will actually transfer electrons and they'll form magnesium oxide, so held together via ionic bonds or an electrostatic interaction, right? This positive negative thing where they attract each other. Okay, so now that we've looked at the overall breakdown of things, remember that we could actually classify matter as either pure substances or mixtures. We could then subdivide the pure substances a little bit further into elements or compounds. Elements can either be atomic or molecular, and then compounds could be molecular or ionic. So I might say something like oxygen. What is that? You'd say, oxygen's on the periodic table, so it must be an element, right? Is it an atomic element or molecular? Oxygen ends in gen, so that must be a molecular element, and you'd be right. Or you could remember, Brinkelhoff, yeah, oxygen's the O in Brinkelhoff, so it must be a molecular element. It's O2. Okay, what if I said something like, how about lithium nitrate? So if I gave you the formula for this, LiNO3, and I asked you, is that an element or a compound? You'd say, well, it has to be a compound because it has more than one element in it, right? And then I'd say, well, okay, you're right. Well, is it a molecular or ionic compound? You'd say, lithium's on the left-hand side of the periodic table, so it's a metal. Nitrogen and oxygen are on the far right, which means that they are non-metals. So this must be an ionic compound held together by ionic bonds or a transfer of electrons. Okay, what about something like sulfur trioxide, SO3? Okay, what do we have here? Well, let's look at this. We have more than one element. We have sulfur and oxygen, so it cannot be an element. It has to be a compound, but sulfur and oxygen are both non-metals, so it must be a molecular compound. And then what if I just said, I've got a roll of aluminum foil here. It's just aluminum. Well, it's not a compound because it's just pure aluminum by itself, right? And you can probably guess that the only one left would be atomic, and you'd be right because it's not molecular. It's not in the Brinkelhoff 7. It's not one of the gens, so it must be an atomic element. Okay, so let's try classifying a few more. How about something like gold? All right, gold, what would we have there? Well, it's an element, it's just by itself, right? It's not one of the Brinkelhoff ones, so this must be an atomic element. All right, so this would be atomic element. I'm just going to abbreviate AE. All right, glucose, on the other hand. It's got to be a compound because it has multiple elements in it, but all of those elements are non-metals, so this must be a molecular compound. All right, how about bromine? Well, I give you the formula Br2, which shows that it's diatomic, but remember that Brinkelhoff starts with Br for bromine. It's also one of the halogens, so it ends in gen, and so this must be a molecular element. Okay, lithium. It's just an atomic element, it's just by itself. What about lithium carbonate? Now we have a metal and multiple nonmetals. Oh yeah, those are ionic compounds. Carbon dioxide has to be a compound because it has more than one element in it, and in fact this is a molecular compound, right, because they're both nonmetals, carbon and oxygen. Sodium fluoride must be a compound as well, but this time it's going to be ionic. Why? Well, because it has a metal and a nonmetal in it. So let's go ahead and look at ionic compounds a little bit further. We mentioned that these things like to contain a metal and at least one nonmetal, right? So if we want to be a little more specific, these consist of anions and cations, right? Remember that anions are negatively charged ions, cations are positively charged ions. Now the number one most important rule of all of ionic compounds is that when you bring these things together, the overall sum of the charges has to be equal to exactly 0. Okay, so let's take a look at this. Notice that we have a sodium, which is a +1, and we have a chloride, which is a -1. And if you have a +1 and a -1, you add those up, it adds up to exactly 0. So sodium chloride is a neutral ionic compound, which is the way it should be. Calcium, on the other hand, calcium is a 2 plus, or a plus 2. Chloride is a minus 1. So if we just had one chloride, that wouldn't work because that would actually not give us a neutral compound, right? So we're actually going to put in another chloride, so a plus 2 and then a minus 1 and another minus 1. Those all add up to 0. So notice that I can actually put in a 2 here in the front of coefficient, and that's why over here you can see that we have 1 calcium, 2 chlorides in order to kind of neutralize each other, to balance this out, to have a neutral compound. Alright, so let's go ahead and try to figure out what the formula would be for the following ionic compounds. So the first thing we need to do is we need to figure out what the charges are going to be. And just as a reminder, in column 1A, these guys like to form a, oh, that's a horrible plus. Let's try that again. Plus 1. These like to form a plus 2. Over here, we would like to make a plus 3. And then we skip column 4A because they don't like to make ions. And then we start going negative 3, negative 2, negative 1, and then we skip these guys because they don't like to make ions either. Alright, so now that we remember this, let's go ahead and take a look at the these elements. So strontium, oh, here we go. Here's strontium, column 2A, so it likes to make a plus 2. So the way I like to do this is to write Sr, a 2 plus, or a plus 2. And then fluorine, oh, way over here on the far right, that's in column 7A. It must be a minus 1. So I'm actually going to specifically write out 1 minus. And then I think the easiest thing to do is to actually take the charges here, and we're going to flip, like crisscross them, flip them, and then turn them into subscripts. So what does that mean? Well, that means that the formula is going to be Sr, and then F, and this is a 2 and a 1, so that we flip that and it becomes a 1 and a 2. Now remember that we don't typically write the 1s, so the formula would just be SrF2, and that would be our compound, because it takes 2 of those fluorides to exactly cancel out the charge on 1 strontium. Let's go ahead and try this with another set of atoms here. So we have potassium, okay, column 1A, so this is going to be a plus 1. We have nitrogen over here, column 5A. Remember that that likes to make a negative 3. Okay, so here's our overall formula, right, Kn. Notice that the metal's always written first and then the nonmetal. So metals on the left, nonmetals on the right, which is fine because metals are on the left-hand side of the periodic table, nonmetals are on the right-hand side of the periodic table. So it kind of makes sense that we would write them in that same order in the formula. Also, when we get to names, the metal's always named first and then the nonmetal. Alright, so over here we have a 1 and a 3. We flip that and it becomes a 3 and a 1. And remember that we don't typically write 1s, so I'm just going to write K3N for that. Okay, and that would be the formula for potassium nitride, and then K3N, this formula formed between potassium and nitrogen. Let's go ahead and try another one of these. This one might be a little bit trickier, but it's not too bad. So we have aluminum, which is over here, likes to make a plus 3 charge. Now these charges, you should become familiar with these so that you can look at the periodic table and quickly know, what the charge is going to be. Until then, you might as well write the charges up at the top of the column. So column 3A likes to always form a 3 plus or a plus 3, and that should help you to be able to quickly remember what the charge would be on these things. Alright, so we also have a sulfur atom. Here's sulfur. Column 6A, so sulfur likes to make a negative 2. So here we have a 3 and a 2. We flip that and it becomes a 2 and a 3. Now there's no way to simplify this, right, and keep them as whole number subscripts. So it's going to take 2 aluminum and 3 sulfides to cancel out the charge on each other to have a nice neutral compound. And remember, that is the number 1 most important rule. All right, so we've been going over the main group elements. Remember that the main group elements are these guys with the A up at the top of the column. But what about the transition metals? Well, it turns out there's no easy way to predict what the charge will be on a transition metal. All right, so remember the transition metals are these guys here in the middle, okay, and they also kind of go underneath this stair step right here. So these guys, these can be a bit crazy. So zinc, notice here's zinc over here, can form a 2+, right? Copper, just right next door, can form a +1 or a +2. Gold, which is down here, can form a +1 or a +3. And chromium can form a +2 or a +3. Silver only makes a +1, and lead makes a +2 and a +4. You can see that this stuff is just madness, right? It's like, who thought of these things? So transition metals are tricky. There are ways to kind of figure out and to understand why they make the charges they do, but it's not easy, okay, especially at kind of the introductory chemistry level. Not going to happen. And so typically I would actually tell you what kind of copper you're working with, right? So I might say, okay, I want you to figure out the formula between copper with a +2 charge and chloride. And so I already told you that copper is a +2, and then you'd say, oh, chloride is a -1. And so you might say, oh, okay, let's see. It's going to be CuCl, and it's a 2 and a 1, so that becomes a 1 and a 2. So I could just simply write CuCl2, and that would be my formula right there. Okay, so now that we've been able to figure out how to actually come up with the formula for an ionic compound, how do you actually name this thing, right? If I have something like NaCl, how do I know the name of that? Well, it turns out that you always name the metal first, or the cation first, and then the anion. Okay, the cation just keeps its name, so that's the sodium atom, so this would just be sodium. And then the anion, we're going to change the ending to IDE. So instead of chlorine, we're going to change this to chloride, and this would be known as sodium chloride. So let's go ahead and look at a couple of these. So we already mentioned sodium chloride, pretty simple. But let's try practicing with a couple more. All right, so LiBr. Li is lithium, and Br is bromine. Bromine becomes bromide. Excellent. Okay, magnesium and chlorine, so this would be magnesium, and chlorine becomes chloride. All right, now one important thing to note here is that there are 2 chlorides here, right? So should I call this magnesium dichloride? No, never say di, right? It turns out that you never ever use a prefix when naming ionic compounds. So remember, ionic compounds consist of metals and nonmetals. So remember that ionic compounds and prefixes, these things do not mix, right? So never, ever, ever, ever use a prefix when naming ionic compounds. When it's just a pure ionic compound, right? Not something crazy like, I don't know, it's like a hydrate or something. Okay, so magnesium chloride, that's it. And the reason for this is that anyone that knows anything about chemistry, if I say magnesium chloride, they automatically think, oh, magnesium is a 2+, chloride is a 1-, and so the only possible formula for this bad boy would be MgCl2. So you don't need to specify that there are 2 chlorides because it should be pretty obvious to anyone that knows about chemistry. So let's go ahead and try a couple more of these. All right, so how about calcium with nitrogen? So calcium keeps its name, calcium, and nitrogen becomes nitride. So calcium nitride. Again, notice that we didn't need to specify how many of each thing we had. It's already given. All right, and then the last one, strontium and iodine. So strontium just remains strontium, and iodine becomes iodide. Oh, and I capitalized there. It doesn't matter. Okay, so strontium iodide. So far, so good, right? So let's go ahead and try going the opposite direction. What if I give you the name, and then you try to give me the formula? All right, sounds like a fair challenge, right? Okay, so barium oxide. So we know that this consists of barium and oxygen. Now, the next step is you'd have to pull out your periodic table, and you'd see that barium is in column 2A, so it must be 2 plus. Oxides in column 6A, it must be a 2 minus. So when we bring those together, a 2 and a 2 becomes a 2 and a 2, but there's no reason to have the double 2 there. We can actually simplify that as just BaO, and that's actually an important step that you should check to make sure that your subscripts are the lowest possible whole number ratio. It has to be a whole number. But just one barium and one oxygen, because a 2 plus and a 2 minus exactly cancel each other out. Now, what about potassium nitride? Potassium is K, nitrogen is an N, nitride. Okay, potassium has a +1 charge because of where it's at on the periodic table. Nitride is a -3. So in this case, we have a 1 and a 3. It becomes a 3 and a 1, which we don't write the 1, so K3N. So that's our formula. What about magnesium chloride? Well, magnesium is Mg, chloride, Cl. Magnesium is a 2 plus because it's in column 2A. Chloride is a 1 minus. So when we bring these two things together, MgCl, we have a 2 and a 1, becomes a 1 and a 2. We don't write the 1, so MgCl2 would be the formula for magnesium chloride. The last one is easy. This one's lithium fluoride. Lithium's a +1. Fluoride is a -1. So +1, -1 exactly cancel each other out, and we have LiF, lithium fluoride. Okay, so we were naming what are known as type 1 binary ionic compounds, which means that the metals, the anions, only form one specific charge. Right? This is something like magnesium always makes a 2 plus. But what about things like copper? We mentioned that copper could be a +1 or a +2. So in this case, it's going to be the exact same set of rules. We're going to name these just as before, right? Where we name the cation first, then the anion. The cation is going to keep its name. The ending of the anion changes to IDE. But there's one difference here. We're actually going to specify the charge on the metal. We're going to use Roman numerals, and we're going to put those in parentheses. So what does this mean? Well, this means that if I put together a compound that's made of copper with a +1 charge, and chloride's always a -1 charge, then I would call this copper chloride. But that's not quite enough information, because this could also be copper with a 2 plus charge and chloride with a -1 charge. In this case, the formula would be CuCl, and in this case, the formula would be CuCl2. They're two different compounds, right, with different chemical properties. So it's important that we specify which one that we want, right? It's like if you walk into a chemistry bar, you say, I want a big glass of copper chloride. They're going to say, well, which type, right? We're going to say, well, in this case, I actually want copper 1 chloride because this is a +1 charge. If we wanted, a big glass of this guy over here, then we should specify that we want, again, copper chloride, but this time it has a 2 plus charge, so we want copper 2 chloride this time. Seems like a tiny thing, but it actually does make a big difference when we are naming these things. All right, so let's try practicing with a couple of these. So the first thing we need to do is we need to actually figure out what the charge is on our, back up for a second. We need to actually figure out what the charge is on our various metals, right? So in this case we have Fe and we have Cl. Chloride we know has to be a -1 because of where it's at on the periodic table. It's in column 7A, it has to be a -1. Iron could be a couple different ones, right? So which version are we dealing with here? Well, notice that if we kind of go in reverse of what we've been doing before, notice that FeCl2, it's kind of like a 1 and a 2. That would make sense that this has to be a 2 and a 1, right? Oops, that looks like an 11. All right, a 2 and a 1. So that would give us FeCl2. Would be the formula, because if we're going the opposite direction, we have a 2 and a 1, becomes a 1 and a 2 over here, right? So in this case, we would actually call this iron, and chlorine becomes chloride. But we do need to specify the charge because there are multiple versions of this, right? So this would be iron 2 chloride because it has a 2+ charge. Now, just so you're aware, there is an older naming system for these compounds. In that system, this would actually be known as ferrous chloride, and iron 3 chloride would be known as ferric chloride. Not a big deal. I don't use that nomenclature personally, but especially if you're going into the field of medicine, oftentimes you'll see like iron tablets will be called ferrous sulfate and so forth. So just be aware that some people, especially doctors, don't like to change over, and so they still use the older naming system. But the vast majority of people would follow what are known as the IUPAC rules, and they would call this iron 2 chloride. Okay, so let's go ahead and try another one of these. This one contains gold and nitrogen. Nitride is always a 3-. Gold, well, in this case, notice that there's only one gold and one nitrogen, which means that the charges have to exactly cancel out. So if this is a 3-, this has to be a 3+, so they can cancel each other out. So what would be the name of this? Well, it would be named gold, and nitrogen becomes nitride. But because this is a type 2, it's a transition metal, we have to specify what's the charge, and in this case it's gold 3 nitride to differentiate from gold 1 nitride and so forth. Alright, let's go ahead and try another one of these. I know you're having fun, right? So we have lead and oxygen. Oxygen oxide we know is a 2- because it's in column 6A. So what's lead? Well, again, notice that it's a 1-to-1 ratio. So the charges have to exactly cancel out. So if we have a 2- here, we have to have a 2+ here. So this would be lead oxide. And then what's our charge? Well, it's a 2+, right? So we would write lead 2 oxide. Ooh, here we have a slightly different version of this thing. Oxide is still a 2-, but this time, what's our charge over here? Well, it turns out if we look at this closely, we'll find out this has to be a 4+. So how do we know this? Well, let's try going in the reverse direction. All right, so if I had PbO and we have a 4 and a 2, that becomes a 2 and a 4. But remember that we have to have the simplest whole number ratio of these. So this would actually become PbO2 because we divide each of these by 2 to simplify it. So here's our formula. So we know that this must be lead oxide. But what's the charge on our lead? It's actually a 4+, right? So Roman numeral 4 there tells us it's lead 4 oxide. So again, let's try going in the opposite direction. So this time I give you the name, you give me the formula. So gold 3 oxide. Well, the nice thing about this is it already specifies exactly what the charge is, right? So gold with a 3+. Oxygen, oxide, happens to be a 2- because it's in column 6A on the periodic table. So we have AuO. We have a 3 and a 2. That becomes a 2 and a 3. There's no way to simplify that, so that's the formula, Au2O3. All right, what about this one? Copper. This time it says copper 1, so this has a +1. And bromide, which is a -1. Oh, this one's nice because it's a +1 -1, so that's just CuBr. They exactly cancel each other out. Let's try this one. Let's try chromium. This time, let's deal with chromium with a 2+ charge, and chloride has a -1 charge because, again, you look at your periodic table, it's in column 7A. It must have a -1 charge. So the formula, CrCl, a 2 and a 1 becomes a 1 and a 2. We don't typically bother writing the 1, so I'm just going to erase that. And you can see now that we have CrCl2. Now what about our last one, titanium 4 sulfide? This one sounds like fun. So we have titanium. This one happens to have a 4+ charge. Sulfide likes to make a 2- because it's in column 6A. So let's go ahead and write TiS here. And we have a 4 and a 2. That becomes a 2 and a 4. Are we done? Not quite, because notice that we could actually simplify these. So if we divide each of those by 2, to simplify it, we would get TiS2, and that's the simplest whole number ratio we can come up with. So this is the proper formula for titanium 4 sulfide. Okay, so up to this point we've been dealing with what are known as monatomic atoms, mono meaning one, atomic meaning atoms, so ions that are formed from just a single atom, right? Now we're actually going to be dealing with what are known as polyatomic ions, poly meaning many, right? So polynomial, many numbers, polygon, many sides, polyana, many annas, right? So it kind of makes sense. So a polyatomic ion is an ion that actually has more than one atom that makes it up. And there's a couple of tables here that you can see. These are also in your textbook. Any typical chemistry textbook would have these things in here. Now notice though, something kind of interesting. So for instance right here with the ammonium ion, what we have is we have a nitrogen, 4 hydrogens, and then overall as a group they have a +1 charge. So that means that as a group they've somehow lost 1 electron. Or if we look at something like this, PO4 3-, which is the phosphate ion, that means it has a phosphorus, 4 oxygens, and then as a group they share a -3 charge. So as a group they've gained 3 electrons. It's kind of like when you're a teenager and you pile into the van with all your friends, and then you're like, oh dude, I could totally go for a pizza. Anyone have any money for a pizza? And you start pooling all your money together and you're like, oh, $5, we can go to Little Caesars, this is awesome, right? So that's the same thing that's happening here. It doesn't mean that the phosphorus and then each of the oxygens has a -3 charge. It means as a group they share that -3 charge. Now I really hate memorizing things. I don't think it's a terribly useful skill in many cases, but this is one of the very few things that I would actually highly recommend that you memorize, because it really is that useful, right? So if you're going to memorize something in chemistry, these charts would actually be a really good place to start. Either memorize it, put it on some post-it notes or something, put it where you can easily find it, tattoo it on your bicep, whatever you need to do, but you're going to need these things quite a bit throughout the entire course. So put a couple stars right here because this thing is important. And you don't always want to be like flipping through your book trying to figure out what the heck is a chromate ion, what's a sulfate, what's the difference between a sulfate and a sulfite, or a hydrogen sulfate and a hydrogen sulfite, right? They are different, and you need to know the difference between these things. Okay, so how do we actually put these things together? Well, it turns out it's the same procedure as before. We're just dealing with polyatomic ions. So just like before, we've got aluminum. We know from our periodic table that aluminum likes to make a +3 charge. And then we look up on our polyatomic ion chart, nitrate, and nitrate is NO3 with a 1- charge. So now we need to put these things together. So just like before, we go ahead and write out Al and then NO3, right? So that's our Al and our aluminum and our nitrate. Now, just like before, we have a 3 and a 1, so that becomes a 1 and a 3. But the problem is, if we write it like this makes it look like we have 33 oxygens, which obviously doesn't make any sense. So it's very important that anytime you have more than one polyatomic ion, you go ahead and put this bad boy in parentheses. And then again, we don't typically like to write 1, so I'm just going to go ahead and erase that there. So our proper formula would be Al parentheses NO3 parentheses 3, right, to show that we have 1 aluminum and then 3 of those nitrate ions. Let's go ahead and try another one. This time we have a type 2 metal, right, a transition metal. So chromium, this one has a 3+. Hydroxide, if we look at our chart or look at the tattoo that you just got, is OH with a 1- charge. Put these things together, CrOH, a 3 and a 1 becomes a 1 and a 3. So 3 hydroxides, 1 chromium, and the charges exactly cancel out. All right, awesome. How about barium and sulfate? Well, sulfate's a 2-. We can look that up on the chart on the last slide. Barium's a 2+ because it's in column 2A. Oh, look, a 2+ and a 2-. Those guys will exactly cancel each other out. So BaSO4. This is barium sulfate. This is that nasty stuff that you have to drink when you go in for a GI X-ray. All right, let's try another one. Ammonium ion. Ooh, that's NH4 with a +1 charge. If you look at that last chart. Ooh, and then we have another polyatomic ion, an NO3, a nitrate. NO3 with a 1- charge. So just like before, NH4, NO3, a +1 and a -1. Oh, that's fine. That means that 1 ammonium ion and 1 nitrate ion would exactly cancel each other out, and we have a neutral compound. And so that's it. All right, so that's it for naming ionic compounds, right? We've learned how to name type 1 and type 2 binary ionic compounds. We've learned how to deal with polyatomic ions, but it turns out that our naming isn't quite done yet. I know this is a long section, kind of bear with me, but the next thing we need to do is we need to figure out how to name binary molecular compounds. Remember that molecular are things that have just nonmetals, right? So something like N2O4, nitrogen and oxygen, both nonmetals. Turns out we're going to name these very, very similar to what we did before. We're going to just keep the first element name, and then we're going to change the second ending to IDE. So in this case up above, we have nitrogen, and then oxygen becomes oxide, right? Now, the difference, though, is that we are actually going to use prefixes. So remember how I said ionic compounds never use prefixes? That's because molecular compounds use prefixes. So those prefixes are reserved for molecular compounds. How can you tell something's molecular? It has only nonmetals in it, right? No cations, no anions, just nonmetals. So we're going to actually use some prefixes here to specify how many of each. So in the case that we just listed above with N2O4, turns out that we're actually going to call this dinitrogen, because di means 2, and I'll show you a chart of those in a second. And then 4 oxygens actually is tetra. But sometimes if we have 2 or more vowels together, we end up dropping one just because tetraoxide sounds funny. So we just call this dinitrogen tetraoxide. Kind of like carbon monoxide, carbon monooxide sounds funny, so we just say carbon monoxide. Another kind of style issue here is that we don't like to use the prefix mono if it's on the first element. So mono means 1, and so theoretically if we're naming something like CO, we should name this monocarbon monoxide, but it sounds funny. Mono sounds like a disease, right? So we don't like to actually begin names with mono. So we just call this carbon monoxide. All right, versus like carbon dioxide, right? So here are the prefixes that you should remember. Okay, 1 is mono, 2 is di, tri, tetra, penta, hexa, hepta, and octa. There are some that go above that, but they're not very common, so we don't need to really worry about this. So let's actually try naming a couple of these things. So we already did this one earlier, right? We called this dinitrogen, and then tetraoxide, so tetroxide. All right, look at this one above it. This one would also be named nitrogen oxide. And this is why we have to specify the exact number of each of those, because this one would be named nitrogen oxide. This would also be named nitrogen oxide. We need to specify which version of nitrogen oxide. So in this case, up here at the top, we have 1 nitrogen, so we should call this mononitrogen, but we're going to leave off the mono because it sounds funny at the beginning of a name. And then 2 oxygens, that means dioxide. So nitrogen dioxide, dinitrogen tetroxide. All right, how about this one down here? So we've got iodine, and we have fluorine, which becomes fluoride. But because these are both nonmetals, we need to specify how many of each of these we have. We have 2 iodines, so we're going to call this diiodine, and 7 fluorides, so that's actually heptafluoride. So diiodine heptafluoride. I actually wanted to name my daughter this, and I thought it would be funny because she could go by di for short, and people would say, "Oh, that's lovely. Is that short for Diana?" And she could say, "No, it's short for diiodine heptafluoride." And my wife vetoed it for some reason. I don't understand this. But let's go ahead and try one more of these. All right, so here we have phosphorus. So phosphorus and chloride, right? Because chlorine becomes chloride. We only have 1 phosphorus, so theoretically we should call this monophosphorus, but we don't want to start the name with mono. So here we have 5 chlorides, so this would actually be pentachloride. So phosphorus pentachloride would be the name. Okay, now I know that this is taking a while, but there's only one more thing that we need to name. We've named ionic compounds, we've named molecular compounds, now we're going to name acids. All right, so acids are actually molecular compounds, right? So this would be something like HCl. So if we see HCl, hydrogen, and chlorine are both nonmetals. So technically this is a molecular compound. But if you actually put this into water, this thing will actually dissolve and it will break apart and behave as if it were actually made of ions, which means that this will actually form H+ ions and chloride ions as soon as it hits the water. So this is a little bit different because it's not quite a molecular compound, but it's not quite an ionic compound. So this is specifically an acid. Acids behave certain ways. We're actually going to go into a lot of detail with this a little later on, a couple sections from now. But just suffice it to say that these like to form hydrogen ions when you put them in water. They taste sour, right? Think of lemons and I don't know, Sour Patch Kids, right? So these are all acids. They like to dissolve metals, okay, and typically the formula starts with H, so HCl, HNO3, HBr, H2SO4, acetic acid, HC2, H3O2. Now, the thing is that there are actually 2 ways of naming these things. One is for what are called binary acids, and the other method is for naming oxyacids. So let's go into practice a little bit of each of these. All right, first let's talk about naming the binary acids. So binary means 2, right? So these are acids that contain only 2 elements. So for instance, our good old friend HCl, stomach acid. All right, so in this case we have a hydrogen and we have a chlorine. So the very first thing we need to do is we need to write the hydro prefix. This is very important. This hydro prefix is reserved only for binary acids, the only time that you'll see that prefix. Next, we're going to name put in the nonmetal name, so chlorine, but we're going to change the ending to ic. So chlorine becomes chloric, and then we're going to add the word acid at the end of the name. So hydrochloric acid would be the name of this thing. Let's try another one. How about HBr? So again, let's put in the hydro prefix to tell us that it's a binary acid. Bromine becomes bromic, and add the word acid at the end of the day, and there we have hydrobromic acid. Alright, so the next thing we need to do is we can actually name oxyacids. As the name implies, these are acids that contain oxygen, right? Hence the name oxyacids. So this would be something like HNO3 or H2SO4. So notice that they're not binary because they don't have only two elements in them, and they have oxygen in there. So these are oxyacids. So these are a little bit trickier because what we have to do is we have to go back to that chart that you tattooed on your bicep, which says the names of the polyatomic ions, right? And we need to figure out what ion these contain. So in the case of our HNO3, this contains NO3 with a 1- charge. So that would be the nitrate ion. Notice that this ends in ATE. If it ends in ATE, we're going to change it to IC. So this becomes nitric, and then we're going to put acid at the end of the name. So this would be nitric acid. All right, let's try another one of these. We mentioned H2SO4, right? So first off, we need to figure out what is that. Well, SO4 2-, that's the sulfate ion. Okay, which ends in ATE, so we're going to change that to sulfuric acid. And this is battery acid in car batteries. Really, really nasty stuff. There's this rhyme. It's like Mother Goose for chemistry kids. I always tell it to my kids. Johnny was a chemist, but Johnny is no more, for what he thought was H2O was H2SO4. I don't know why they can't sleep. But anyway. Okay, so naming oxyacids is an important thing. We mentioned that this is HNO3, contains nitrate, so therefore this is nitric acid. Let's go ahead and practice a couple more of these. So we already named this one here, right? Oops, back up for a second. So we already named this one right here. We said that this was sulfuric acid. So let's go ahead and try naming a couple more of these. All right, how about this one up on top? First off, is it binary or is it an oxyacid? Well, it only has two elements, so it must be binary, right? So binary means that we have to include the hydro prefix, and then this is iodine here. So instead of iodine, we're going to call it iodic, and then add the word acid at the end. So hydroiodic acid. Not hydroidiotic acid, almost. All right, so let's try another one. All right, how about this one here? Only two elements, right? So this is binary. It does not contain oxygen. It's not an oxyacid. So again, we have to put in the hydro prefix, and then sulfur becomes sulfuric, and then put the word acid at the end. So hydrosulfuric acid versus sulfuric acid. So you can see that it's important that we name these precisely, because this hydro prefix told us that this is the binary acid containing sulfur. Sulfuric told us that this is the oxyacid containing the sulfate ion. All right, let's try this one here. This is an oxyacid, obviously, contains oxygen. And NO2 with a 1- charge, that looks a lot like nitrate, as in the previous example on the last slide, but that's not actually nitrate. That's the nitrite ion. Okay, this ends in ITE, so our rules for oxyacids say that that should become an OUS. So instead of nitrite, this becomes nitrous, and we will write the word acid at the end. Nitrous acid. All right, so that kind of wraps it up for this very, very long and very important section about naming things, figuring out the formulas for ionic compounds. There's a lot of important information here. Now, I'm going to include this chart. Some people kind of freak out when they see this. I personally find it kind of useful, but feel free to use or do not use it as you so desire. But this is how I actually name various compounds. So, for instance, let's say that I had something like NaBr, and I was asked to name this thing. Well, what I would do is I would go down here and I'd say, what does this contain? It contains a metal and a nonmetal. So it's not an acid, it's not a molecular because that's nonmetals only. Oh, metal and a nonmetal, that means that this is ionic. Then I'd drop down and I'd say, is this a type 1 or a type 2? And I'd say, oh, it's type 1 because sodium is in column 1A. I know exactly what that charge is going to be. It's going to be a +1. So that means it's a type 1. And so it says, well, all you have to do is put the cation name, which would be sodium, and then change the ending of the second name to IDE. So bromine becomes bromide. And I just named this thing sodium bromide. Let's try another one. Let's say that you have something like I don't know, like HF. All right, well, this doesn't contain a metal and a nonmetal, so it's not ionic. It does contain only nonmetals, but notice over here that it's actually an acid because it's H and then a nonmetal, right? Now, is it a binary? Yes, because it only has 2 elements in it. So this specifically tells me that I need to put in the hydro prefix, hydro, and then fluorine becomes fluoric, and then put the word acid at the end of the name, and this is hydrofluoric acid. All right, this is actually a really nasty acid. This is actually absorbs right through your skin, actually dissolves your bones, and so you remember in Harry Potter when his arm bone dissolves and he's all floppy? You'd be like that, except you'd be dead. Scary thing is actually sold at craft stores. It's the acid that's used to etch glass. So they say, you should make sure to put gloves on when you do this. They should have a giant warning label that says, be careful with this. This will eat through your bones and dissolve you, and you will be dead. Okay, pretty scary stuff. All right. So on that happy note, let's go ahead and finish up this section. Thanks for staying with me. So this has been a long section about bonding, and hopefully you've survived it. If not, you're going to miss this next card trick. So in chemistry, it's very important that you give the correct name, right? If you say lithium phosphate, you actually mean potassium carbonate. You walk into a chemistry bar, you order the wrong thing because you gave them the wrong name, and there could be problems, right? But with magic, obviously, I can read your mind even through the computer, so it doesn't really matter what name you say. So let's go ahead and see this in action. Let's say that you take a card, okay, any card you want. Let's say this one, right? And now let's go ahead and find out if you can lie to me. I'm going to spell lie, L-I-E, and then I'm also going to spell truth, T-R-U-T-H. And then you're going to come up with a name. It could be anything, the three of diamonds, or 2 of hearts, or whatever you want. Let's say ace of spades, A-C-E. That's easy. Spell that out. And now of is easy, O-F. And you said ace of spades, right? So spades, S-P-A-D-E-S. So it could be any name you wanted. Let's find out the truth. T-R-U-T-H. And sure enough, if we flip over the top card, it's got to be your card, right? Awesome. So again, make sure that you give the right name when you're talking about chemistry.